So this chapter discuss the open channel. Means like you have a flow of liquid that has a free surface. It means there is interface between one fluid to the other fluid. And the most common application is the flow on the channel with the fluid is water, liquid, and another fluid is air. So due to that flow conditions, the the development of the velocity distribution is not constrained by the enclosure. Unlike in the pipe flow, you have the pipe wall as the enclosure, and that will limit the development of the velocity profile. Also, another characteristic is there we can consider no pressure force that push the liquid. Usually the liquid flow by the gravity, by the depth difference from the upstream to downstream. So that will modify a bit on the continuity equations and also the energy equations for this kind of flow. But they have a lot of applications. For example, on the flow on the dam, on the river bank, on the channel, open channel like gutter and so on. So it's also have an important applications. Okay, the characteristic of the open channel flow is they have the it's not completely filled by the fluid, and then there is a free surface existing between the flowing fluid and the fluid above it. And see, the main driving force is only the gravity forces due to the difference on the depth or on the height. And this force is equal or balanced with the shear force between the fluid and the channel surface. Okay, and also there is no pressure force, because otherwise then you have is the force will be directed to any directions, right? Since it has an open channel, then it will create wave and so on. Otherwise, then if it is like flowing as usual, there will be no pressure force that throw the fluid through the channel or conduit. And then for the steady, fully developed channel flow, the pressure distributions within the fluid is merely hydrostatic, so only functions of the Z or the depth. Yeah, this is examples: creek, river, gutters, canals, drainage ditch, sewers, gutter along roads, refueled and at the parking lot, and then also flow in chute of water rights and so on. Okay, so if we try to classify the open channel flow, there are several approach. Let's call it type 1 classification. So this is based on the flow conditions. We have a uniform flow where the depth of flow does not vary along the channels, or dy dx equal to 0. But total, of course, total height is decreasing, but the depth, as you can see over here, is remain the same along the flow. The depth, the y is the same. So we have a uniform on that case. And we have the second kind of non-uniform. The non-uniform consisting of rapidly varying flow, or RVF. So this is, for example, this is also RVF. So there is change on the flow depth. As you can see, you have a different y at this point and y at this point. Also y in this and y over here is different. But this is on the short distance, like dy dx close to 1. There's also gradually varying flows where the flow depth changes slowly with distance, like this one. The flow depth changes slowly because the profile and also the relative depth over here have gradually changing at distance. So the RPF usually due to disturbance, while the gradually varying flow usually due to the slope. So the slope usually measured by dy dx. So if you have like this, for example, so this is the y and this is the x, for example. So that dy dx is the slope, tangent of the slope. Okay, another classifications of the open channel flow is based on the Reynolds number. Now we have also different threshold number for Reynolds numbers on the open channel flow, where you have a considered laminar flow at about less than 500, the transitional flow from 500 to 12,000, and the turbulent flow if it is above 12,500. Here we introduce the hydraulic radius instead of the diameter or the length. Remember, on the pipe flow, you have rho phi d over mu, or on the flat plate, for example, rho phi l, as the length divided by mu. So this is characteristic length. While on the open channel, we use the hydraulic radius of the channel, where RH is defined as the area divided by the wetted perimeter. So if you have, for example, like this, the flow is going into our directions. Then you have the area here, and you have the wetted perimeter as the perimeters over here. Okay. So since most open channels involve water, which considered smaller viscosity, there are many open channel flow that have laminar. For example, on the big dam, waduk, you will have that laminar open channel flows, or a big gutter with small slope, then you can have a laminar flow. Okay, classification number 3 is based on the Freud number. So the Freud number actually giving you the ratio between the inertia, the v over here, velocity, and the characteristic length, or the g value here, we call the external field. In this case, external gravitational field. So Freud number is equal to the velocity of the flow divided by square root of potential gravity times the characteristic length. So we can divide this into critical flow, where the Prot number equal to 1, subcritical flow, where the Prot number less than 1, and supercritical flow, where the Prot number is greater than 1. So yeah, the Prot number is a dimensional number defined as the ratio of the flow inertia to the external field. In this case, usually simple gravity like this one. Okay, we can continue. So first, the surface wave concept. If you have an open channel flow, there are often wave at the surface of the flow. This can be solitary on a single surface. For example, one rock thrown into the water, and then you will have the surface over there. But sometimes it will also traveling together, just like sinusoidal. So we have a free surface at the open channel flow, and then the surface can change into various shape. So it's not following the channel shape. And it's usually distorted into ever-changing patterns, associated with the surface waves. And then we can actually try to analyze or to calculate actually the wave speed. In this case, c. If we derive to find the wave surface velocity by utilizing the Bernoulli equations, but without the pressures. Remember, you should have like usually the pressures over here, but for open spread there is no pressure. So only the velocity and the y is the z actually. This is the height from the datum z. Since there are constants, and then if we try to derive that, to differentiate this, as we have an increasing dv over here, this will become into these equations as a very small dy over here. While for the continuity equations, area times velocity remain the same, or py times py is the velocity times, since the area is somewhat shaped like this, so the width remain the same. So the only difference is only this y over here. So phi times y is actually coming from phi times y times, let's say, the width, for example. But we can cancel them because there's a, while y is varying because there is a surface wave over here, dy over here. If we derive that into this, then we can combine the two equations to get p equal to square root gy, or in our case using c equal to square root qi. So this is the surface wave traveling velocity. Okay, if we analyze more, and also the experiments show that the wave speed for finite size solitary wave is not only that part, it's to be in this shape or in this form, which is greater than square root gy only. So we add this additional component term to calculate the surface wave velocity. So the larger the amplitude, the faster the wave travel. So the dy. So if you have a bigger surface wave, then it will travel faster. Okay. We have also continuous sinusoidal shape wave speed, where, for example, on the oceans, surface ocean, or on the river with the continuous wave, then we can still develop or derive the equation for the speed. To consider combining wave of various wavelengths and amplitude, and also delta y. And the wave speed varies with both the wavelength and the fluid depth. So we can use these equations to get what's the traveling speed of the surface wave. So there is derivation steps on this one, but I think I want you to notice the only additional variable than the solitary wave previously is only this, the wavelength. So the wavelength is the length from one to the repetition point to the next wave. So this is the lambda, the wavelength, from top to top, or from the valley to valley. This is also lambda. So that's the only difference to our previous solitary wave. Okay, any questions at this point?
No, sir.
Okay, let's continue. Now, a concept that is used on the open channel flow is called the specific energy, and that's what we're going to discuss on this one. Go back to the Bernoulli equations, except for these applications that we won't have this P force. So the equations involving this. Previously we used this Y, but the same concept on this one. And if we introduce the Z, we can have the Z can be divided into the depth of water and the depth to some reference or datum Z0 over here, because we have a different depth, for example. Different depth because of the natural cause or because of the shape of the channel itself. So this is to account for the changing of the depth. Now we can use this specific energy concept. This is the component of the total energy that only contains the flow depth and the velocity term. So it's actually based the same Bernoulli equations, but we express it as specific energy. Although this is actually the unit is head yeah, pressure heads on this one. So the E value is called the specific energy head, of course, and still no pressure component on this one. So for the open channel flow, if you ask about the specific energy, is equal to the Y plus V squared plus 2G. So another way to express it is using the flow rate. This is using the velocity. So this is the velocity. But for some applications, we more concerns on the flow rate. This is it. Yeah. We can redefine the specific energy in terms of discharge Q. And then we can substitute the velocity with the flow rate, where with this equation V equal to Q over A. So the velocity become, since this is V square, then you have Q square over 2G times S square. So actually this is the same specific energy, but now we express it as the flow rate. And then if we have the area, we can modify the previous equations. If we have the same the flow rate over the unit width, so the area, for example, base times the height, so only the height part is left after we divide by the width. Or we can now have this specific energy equation in terms of specific width over here. So you before we have Q square over A square. Now we can have Q square over Y square, since considering the unit equal to 1. So this is a discharge or debit per unit width. But there is no change on this specific energy equation. Okay, we can plot the specific energy with the depth. So if we plot the specific these equations, or this previous one in terms of the width become these equations. So this one over here, we will have this plot over here, specific energy or specific head. As the depth increase from 0, the specific head decrease, and then at some point at minimum E, as the depth decrease, this energy also increase. So it formed this shape. So there is a minimum specific head or energy for every open channel flow. So at this point, dE over dy equal to 0. So there are two possible depths for the same specific energy. Like this, between this point and this point, you will have the same specific energy, although at different height. Okay, so by knowing this, by plotting the specific head or specific energy into this plot, we can determine at which point the depth will increasing the depth, or the more the deeper the channel. Okay, when it's going to decrease the specific head, and it's increased at some point. Okay, the point is you can calculate or you can plot the specific energy based on the, because if you know what's the legend of the the depth of the and also the flow rate over here. You can plot this one. But in the reference, we plot this a little bit differently. So we put the y on the vertical axis, and it's more intuitively correct. So this is the depth, or y over here. And the energy is on the horizontal. So it's actually similar as you go deeper. So you can imagine the flow as increasing depth. So it's become, for example, if you have a slope, this is the water level, for example. This is the water level. And you have the channel with the slope. So you're going to have, so this is y at this point, and y also at this point. As it goes deeper, at certain point of the depth, you will have the specific energy minimum. As you go further, the specific energy will increase over there. We can actually solve the critical depth where we have minimum energy. Here. So the critical point occurs when the slope of dE dy is equal to 0. So we can just take the derivative of E with respect to y on y, okay? And then we can have E equal to y plus q square y minus 2 over 2g. Then dE dy is equal to this. And this equal to 0. Or y critical can be obtained when q square over g to the power of 1/3. That will be your y critical. So at this point below this depth, the specific energy is going to be greater and so on. So it will be like this, like what we have over here. So this is y and this is the E. At certain y, we have this minimum specific energy. If we try to express that into a velocity component, so this is still in the form of the discharge or debit, right? But we can also use the velocity component on it that will have this equation for the velocity. So v square divided by g y critical is equal to 1. And you can solve for y critical in terms of the velocity. So these sections give you information on how to calculate the specific energy and also the critical depth of the flow, which have the minimum specific energy or specific head on this one. Okay, we can continue, and then because this is relevant to the Freud number, this one. So this equation is actually a square of the Freud number, because the Freud number is equal to phi divided by square root g times y. So it's really relevant to the Freud number. So this also defines what's the critical flow, supercritical flow, and subcritical flow, as we defined on the classification of the open channel flow previously. So phi square over gy is the square of the Freud number. And this is the ratio of the kinetic to potential energy. And as we discussed before, it's used to characterize open channel flow for the subcritical, supercritical, or critical flow. So at the minimum specific energy, the Freud number is equal to 1, which is the definition of critical flow. Above that is supercritical, below that is subcritical. So this is relevant to the Freud number and the specific energy topics on this one. So flow deeper than the Freud number, or of Freud number equal to 1, it means it's larger depth. So if we see over here, if this is greater than 1, then this value is small. If you want to have greater than 1 or supercritical. So it's large depth in the nominal. So Freud number is equal to Freud number is less than 1 is called the subcritical flow. Yeah, and it is deeper and slower. For shallower than Fr equal to 1 is called supercritical or shooting flow. It is slower and faster. Let's bring the equation to this slide so you'll be able to. Here you go. So if y critical, if y is bigger, if y big, then Freud number less. Y big means deeper, and velocity become, if you want to have low Freud number, velocity is slower on this one. So if you have a deeper and slower flow, you have a subcritical flow. If you have lower and faster flow, you have the supercritical one. Okay. And there's a note: never design a channel on a slope that is near critical, because then you will have this unpredictable water surface. Okay. Another this unpredictable is for example is what we're going to discuss, the hydraulic jump on this one. Any question until this point? The concept of specific energy on the open channel flow and the classification based on the Freud number. No questions? Okay.
Currently, sir, most of this is just using Bernoulli principle, kan?
Yes.
Tapi for the previous one, how to calculate the Reynolds number? So the L is the perimeter of the surface, kan?
The L on the Reynolds number. Oh yeah, the calculation of the Reynolds number. Yes, it is.
Okay.
The characteristic length, or we call it the hydraulic. So this is the difference thing. It's not only parameter. So the Reynolds number over here that we use to classify the laminar or the transitional flow, it's not using L, but this is using radius, hydraulic radius. And the hydraulic radius is equal to the area divided by the weighted perimeter. So the area of the flow, if you see the flow, if you cut the flow and then you see from the direction of the flow, you will see an area over there. And the weighted perimeter is the perimeter that has the water on it. So it's not the length of or not only the parameter. So RH in this case is the area divided by the weighted perimeter. If you remember the hydraulic diameters, when you calculate on the pipe flow with non-circular pipe, for example, non-circular conduit, for example, this one, then the calculation of Reynolds number is rho p. This is dH, hydraulic diameter divided by mu. So this is the same concept, except that for the open channel flow we use the RH, the radius, hydraulic radius. Is that clear enough?
Okay, Pak.
Yeah.
Weighted parameter tuh weighted perimeter is the surface in contact with the water kan?
Yes, it is. Okay. Okay, we were at the critical flow. Now we have if we have a change on the Froude number, suddenly we will have what we call the hydraulic jump. So as shown in this figure, so there's a change of the Froude number from shallow fast to deep and slow. We're going to have this jump over here, and it is actually try to be avoided, because then you have this is unpredictability of the water. So at this transition, the flow has to suddenly change from one flow depth to the other. It forms a jump between one and the other, and then we can actually try to predict this or to calculate the ratio during the hydraulic change. So the ratio of the depth during the hydraulic jump like this, if you see here, so we try to get to this point, but it's not going to be directly to this from Y1 to Y2. So this is Y1 and this is Y2, but you're going to have this regions with the very turbulent surface over here. And the ratio of the depth of this can be derived into these relations. So the way you're using this, if you want to predict what will be the height, or usually the Y2, you want to know what's the Y2. So you're given this Y1 over here, given flow, so you can calculate the Froude number. And you have this gate, for example. And then this will have a hydraulic jumps into the Y2. And you want to know what's the Y2 over here to, for example, to avoid some height that you want to you don't want to happen. So you can calculate what's Y2 using these equations. Okay, any questions this point? Good, let's continue.
Tapi in this case, Pak,
Yeah.
Y1 is the critical Y. Not necessarily the critical Y.
Not necessarily any Y that you. I mean, if you have experienced this, you actually want to avoid this hydraulic jump, or at least you want to anticipate this, and we can anticipate this by using these equations. The Y1 is the source. This it happens when you have change of the Freud number from the less than 1 to greater than 1.
Okay.
Okay. Now this is a different topics. It's called the Chezy-Manning equations. This is sorry. So this is used to estimate the velocity if you know the flow characteristics. So it turned out the interaction between the channel walls and the fluid is difficult to predict using the viscous theory. So what we come up with is an empirical equations relate the flow characteristic and the velocity itself. So these Chezy and Manning equations give you the information on how to calculate the velocity and the flow characteristics. So we have RH is the hydraulic radius, and S0, SO is the slope of the channel, means Y divided by X. So these, if we have a changing
changing height, yeah.
Changing depth, for example, Y value. So S0 is equal to Y over X. If that's for example, pretty small on this one. Okay. N value depends on the surface condition of the channel. So this is the Manning resistance coefficient, and it's dependent on the surface matter of the channels, whether parameter, and is obtained from experiments. The unique thing is this is actually developed for SI unit, and it's actually dimensional, so it's not a non-dimensional N values. So since it has been used extensively, we don't change the equations. But if you work with the IP unit, then you should put 1.49 in front of it. This is actually a conversion unit. Conversion unit between SI and IP unit. So if you use the Manning equations, you have to aware of the units used for RH and the slope. The N value will remain the same, but if you use with the IP unit, you need to put times 1.49 over here. Okay, let's try to put it into use, these equations. Oh, this is the N value obtained from the experiments. So you have natural channels, clean and straight, sluggish with deep pools, major rivers, for example, flood plains, excavated earth channels, or artificially lined channel for the gutter and so on. Glass, brass, steel, clay tile, brickwork, and asphalt, and so on. Rubble masonry also used over here. Concrete finish or unfinished is also here. Okay, let's try to use it in our case. For example, if we have this kind of channel, is a trapeziums actually, trapezoidal cross sections, and the bottom drops 1.4 feet per 1,000 feet of length. So this actually tells you the slope. This tells you the slope. And then we need to determine the flow rate if the canal is lined with the new smooth concrete, and determine also the plot number. So by knowing the slope, for example, on this case, we able to calculate the flow rate or the velocity another way around, because the flow rate is the velocity times the area itself. Okay, so the solutions is given here. Please note that since the unit is given in the IP unit, feet per 1000 over here, then you need to put this additional coefficient K 1.49 in front of the equations. So phi equals, so this is the stage remaining equations. If you want to calculate the flow rate, so the Q is equal to phi times A, or 1.49 times the area times the hydraulic radius and this slope divided by N. N is obtained from the table. So the slope is equal to 1.4 feet divided by 1000 feet, 0.0014. And now the area is equal, the area of trapezium is equal to the base, the summation of the base times the perpendicular height divided by 2. So we have, this is 12 feet, and this is, this is equation to get the this line over here. You can solve this actually to find what's the area of it. 12 feet times 5 feet plus 5 feet times 5 over tangent 40. That will give you this, the line over here. This one over here. Since you're going to need it to calculate the area, you can derive this. The area of the trapeziums is equal to half. This is the, let's say, the base times the plus the top, and you multiply with the h. H is y in this case, 5 feet. The base is 12, and the top is equal to base times this part here. Plus, sorry. And we can get that from the relations over here. So let's say you find the area, and then the weighted perimeter, and now you, oh yeah, the weighted perimeter is only this part, yeah, sorry, I just need to define this one. So 5 over sinus, so 12 feet is this one over here. Let me use different color to find the weighted perimeter. So this is 12, and this is 5 over sinus 40, and you multiply with 2. So this is your weighted perimeters, this part. So you find the hydraulic radius as A over P, 3.25 feet, and then you just plug it into the equation. So this is the area, and this is the hydraulic radius, and this is the slope. And N obtained from the table. As this we have, this is 915 cubic feet per second. You can always change it into cubic meter per second, for example. And the Freud number can also be calculated using these equations. First, you need to find what's the velocity of here. Okay, any questions?
Sir, for the n value, is it because it's concrete?
This is a new smooth concrete. So if we take a look on the table here, this is concrete finish 0.012. So from this table over here, we have it here, 0.012.
Okay.
I think the challenge is to find the area, but you can always do that using trigonometry and so on, or algebra and so on. So from here, actually, we can from looking at the slope, for examples, and the depth, we can try to estimate the flow rate and the velocity of the flow. So this is pretty useful equations to get. If we have the information of the geometry of the channel, then we can derive to find the velocity or the flow rate over there. Okay, no questions? Okay, we're going to, yeah, let's try to modify a little bit. Now, over here, we know the geometry and we want to find the velocity or the discharge or the debit. Another case is we want to, when we design things, we want when we design the channel, we actually doesn't know the geometry, but we know the debit. I mean, we want to have a certain debit. And this is given in this kind of problem. If you want to have like 10 cubic meter per second of flow rate, for example, to run a turbine to get that Q, how much depth you need for the channel? So this is another question that rises up that can be solved using the Jesse-Manning equations. So let's say we have the same shape but different geometry, different height in our case. We don't know what the height is. We want to determine what the height is, so we can have the debit, for example. But this time the lining is not concrete. The lining is a weedy. It's like you have apa namanya weeds ya, tumbuhan di dasarnya, on the bottom of the channel. And the question is how much depth we should have in order to have 10 cubic meter per second flowing in the channel. So that was the question. So again, we can use the Jesse-Manning equations. First, we need to calculate what's the hydraulic radius on our case, but we don't know yet what's the area. So the flow area based on the trapezoidal formula for the area is equal to half times the height times the sum of the base and the top over here. We don't know what W is, but we can derive that W is equal to 3.66 this base plus 2 times this part, right? This part. So this is 3.66, but this one is equal to y over tangent 40. We can get that from the trigonometric one, since we know the y over here. Y over tangent 40 is this part. You multiply by 2, you add with the base, you have this W over here. if you substitute this into these equations, you can get the area, or if you simplify into this. So A is equal to 1.19 y squared plus 3.66 y. Leave it there because we don't know what's y. We want to know what's y is. The perimeter itself, the perimeter is this, it's still the same, right? Like the previous one, except we don't know y. So it's going to have y over here. So the radius, hydraulic radius A over P equal to this, A divided by the P. So we get, oh yeah, the same slope. This has the same slope. So slope remain the same, as 0 remain the same. Q equal to 10 times, oh, the K value is equal to 1 since this is on the SI unit, so you don't have to multiply with 1.49. So I still use 1 over here, and can be obtained from table 10.1. Let's take a look for the VD surface foot planes. 0.03. So this is your surface conditions over here. 0.03, go back over here. So the 0.01 divided by 0.03 times the area, you can just input over here, times the RH, the power of 2/3, times the slope, 0.0014, I believe, 0.0014. And then you can solve actually for y, because if you plug in all the number, you end up with the one variables, although on the polynomial equations, this one like this. But you can always solve it using computer or calculator to get y equal to 1.5 meters. So this will give you, if you need, if you have certain geometry of the channel, and you want to have certain discharge or debit, then you need this height. So that's a example of the use of the Jesse-Manning equation on this one.
Sir?
Yeah, go ahead.
So in here, the the radius, hydraulic radius will be to the power of 2/3 kan?
Yes.
The hydraulic radius will be to the power of 2/3 kan?
That's true.
Jadi this equation yang 1.19 y squared plus 3.66 y divided by 3.11 y plus 3.66 ini harus di pangkat 2,2/3 ya?
Well, let's see, if you input these equations, I think what you're going to end up is, since you also include this part over here, the area. So if you have 1.1, this is area, so this is area, right?
Yeah.
Still the area, the same like this. These are the same. Times the, oh, what you do actually, A times A over P. This part over here. Oh, sorry, this should be 2/3, yeah? So you're going to have A to the power of, let's see.
A divided by P to the power of minus, A to the divided by P to the power of 1/3 ya?
Yeah, this is P to the power of 1/3, 2/3, yeah? And here, if you put them, they'll become A to the power of 1 plus 2/3. So 5/3. isn't it?
Yeah.
And then, so this time the slope is given. So y is end up at 5 over here.
We cube it by 3, all of them. Kan?
So a over p to the power of 5. No, it should be 5. This is 5.
A5 over P2 ya.
But there is no p over here. Where's the p over here? Oh yeah, okay. So this is actually p, right? This is p.
Oh.
So you have this. Yeah. So this is algebraic. So you can so you end up with this. Let's see. This just a little bit over here. So 10 equal to, or any constant value number, yeah, is equal to something. It's actually from the 10 over here. This become a to the power of 5 divided by p to the power of 2, and then you multiply this by 1/3, yeah. Okay, and then if you take this one, which is you cube this constant, then you end up with this equation actually. So you can have this equation by having this. If you work on this, then you can have this kind of equations. Is that clear enough? Because
Okay,
you end
Pak.
up going, is this going to be a constant, right? And if you take out, let's clear this up. This is a constant, and this is all constants over here. SO to the power of half also a constant. So you're going to have this A times RH to the power of 2/3 equal to a constant. If you substitute this RH with the A over P, like what we did, we will have A to the power of 5 over P, over, yeah, P to the power of 2, and this become 1/3 equal to constants. And if you have A to the power of 5 divided by P square equal to another constant, since you just to the power of 3, right? So you can have A square minus C P square equal to 0, which you have this over here. Sorry, not square, but 5 to the power of 5 equal to 0, just like this equations. So this is the constant that we have. Is that clear enough?
Yes, Pak.
Okay. So I think that's for today. We have discussed the open channel flow, the characteristic of it, the classification. We can take a look on that flow into 3 classifications based on the uniformity. You have uniform flow or non-uniform flow based on the Reynolds number, whether it's laminar or turbulent flow, and also based on the Freud number, whether it's critical, subcritical, or supercritical flow. We also discussed on the surface wave speed, either that's a single surface wave or sinusoidal surface wave. We can calculate the speed of the wave, and then we discuss the concept of specific energy or specific head and how it relates with the depth. And then we also discuss the hydraulic jump. And the last one we discussed on the Chesney-Manning equation to calculate the velocity or the discharge of the given flow, given channel flow. Any question until this point?
Not yet, sir.
Okay, so this is what I'm going to the topics of this is the end of the topic actually on the open channel and also on the course itself. On the lesson plan actually I put in compressible flow, but the discussions on the I discussed with Prof. Budiarso, Prof. Warijito, Parido, and so on, that the compressible flow will not be included in the basic fluid mechanics course. We are changing the curriculum. It will be discussed on the aerodynamics elective course. So, but it makes sense. For example, even the air application, we can still incompressible. We can still use the incompressible approach when the velocity is close to Mach 1, but if that's higher, then but this application that involves velocity greater than Mach 1 is greater than 300 meter per second is on the aerodynamic, usually on the aerodynamic applications. So that will be on the discussions on the aerodynamics elective course. So this concludes actually the material from this course. We still have 3 meetings actually on Wednesday and another 2 meetings next week. What we're going to do is do a review. On Wednesday, I think I will give you homework related to this open channel flow to make you familiar with some of the variation of the problem that you can solve. And then the next 2 weeks, I will give you a practice problem with the given solution, so you'll be able to practice on the solution and the problem and solutions.
Sir?
Yeah.
The lecture is moved from Thursday to Wednesday because of Waisak ya?
Oh yeah, tomorrow Waisak ya on let's say.
Usually kita Thursday ya?
Yeah, we normally do class on Thursday.